Okay, so we're having Ariel Salort, who will be speaking about asymptotic results in magnetic Orlicz-Sobolev spaces.
Okay, thank you. In this talk, I want to share with you, some results about the bibliography about asymptotic result for fractional spaces. Yes, in the limit cases when S, which is a fractional parameter, goes to the limit cases 0 and 1. Yes. Then I want to introduce some possible generalization of these kind of spaces. Yes, more precisely, the magnetic version of the fractional spaces. Yes, I want to share with you some results about these 3 papers. Yes, in the first one, we introduce a generalization of the solar spaces in which the non-local gradient has a behavior more general than a power. And then we study the behavior when S goes to 1. In the second paper, we introduce a magnetic version of these spaces and the behavior again when S goes to 1. And finally, in the third paper, yes, we study the behavior when S goes to 0. Okay. So first, before stating the results, I want to spend some minutes, yes, with some definitions and basic facts about the P Laplacian and some generalization of this operator. Yes, recall that the usual P Laplacian is defined as the divergence of the gradient to some power. So this operator is local in the sense if you want to compute the P Laplacian of a function u at a point x, yes, it is enough with information in a neighborhood of the point. So this operator has a power behavior in the sense the gradient is to some power, and the space for defining solutions, weak solution of this type of operator is the space W1P, yes, the Sobolev space. So at this point, you have 2 possible generalizations of the P Laplacian. If you keep the locality of the operator, but you replace the power behavior of the gradient with something more general, yes, you obtain this operator, which is the G Laplacian. Yes. The function small g is the derivative of the function capital G. Capital G is a Young function, which basically is a function which in 0 is equal to 0, is increasing and convex. Of course, you have powers and you recover the P Laplacian, but you can admit, for instance, powers time logarithms, exponentials. These 2 functions, for instance, satisfies what is called the delta 2 condition, which roughly speaking means that the function can be bounded with a power. Yes. So this one does not satisfy the delta 2 condition because the exponential grows faster than any power. So the usual space where you work is to define weak solution of this operator is the space W1G. Yes, in a moment, I want to define it more precisely. Yes, another possible generalization of the P Laplacian is when you keep the power behavior of the gradient, but you change the locality to non-locality. So non-local in the following sense: if you want to compute the fractional P Laplacian of u at a point x, you need information coming from the whole space, yes, because of this integral in the whole Rn. So the G Laplacian we have so that is defined this way, yes, and the space W1G, the space in which you define the weak solutions, is the set of functions in an Orlicz space LG, and the same for the gradient. Yes, LG is a space which is defined as the set of functions for which this quantity is bounded. Yes, this quantity in the bibliography is called as a modular. Yes. In the case of the Lebesgue space LP, yes, when G is T to the P, for instance, this quantity is like the norm to the P. But I think that the big difference with the Lebesgue space is that you cannot define the norm in terms of the modular. Yes, because of this function, yes, because it's general, And this modular, this quantity, don't satisfy the triangular inequality. So you have to define the norm in a more suitable way, for instance, in terms of the Luxembourg norm. In a moment, I'm going to come back about this. So regarding the fractional P Laplacian, yes, I mentioned before, the suitable space where to define weak solutions is a space WSP, which is the set of functions in LP for which this quantity, which is a kind of fractional derivative, is an LP with respect to some measure. Yes, here this number S is in somehow, yes, the amount of derivatives in the space. So when S is equal to 1, you expect to recover the space W1P, yes, functions in LP and the gradient in LP. And when S is equal to 0, you expect to obtain the space LP because the function is LP and there is no derivatives. So the biography about this space is the fractional spaces, and the W1G is now classical. I have a lot of books and papers about this. So now I want to recall some results about the asymptotic behavior of the spaces WSP, as I mentioned before. So first, when you have P equal 2 and you send S to 1, yes, you expect to recover the space W12. Yes. Sometimes in the biography, this space is called HS, yes, because of the Hilbert space in the case P equal 2. And this result was proven to be true, yes, and it is known from the 60s. Yes, for instance, you can find the proof in the book by Stein. Yes, the conversion of these spaces is in the following sense. If you take the seminorm of this space to a square, and you send S to 1, this quantity blows up. But if you multiply it by a correction term, yes, y minus S, this quantity goes to the seminorm of the limit space to a square up to some dimensional constant. Yes. The proof basically is given in terms of the Fourier transform. Yes. So this kind of analysis, in order to obtain these asymptotic results, is only true when P is equal to. So when P is different than 2, you cannot use that technique. Yes, and the conversion of the space WSP to W1P, yes, for any P bigger than 1 was proven in 2001, yes, by Bourgain, Versis, and Mironescu in a very famous paper. Yes, and the conversion is in the same sense. If you take the seminorm to the P times 1 minus S, this converges to the seminorm of the limit space up to some constant. Yes. The case when P is equal to 1, yes, was covered by Juan Davila in 2002. And he proved that the space WS1 goes to the space of functions of bounded variation. And the conversion is in a similar sense. Yes. So up to here, the behavior when S goes to 1. Yes. What happened when S goes to 0? Yes, the answer was given by a very famous paper by Masia and Shaposhnikova in 2002. They proved that for any P bigger or equal than 1, the space WSP goes to the space LP when the fractional parameter goes to 0, yes, what I mentioned in the previous slide. And the conversion is in a similar sense. Yes. The seminorm blows up when S goes to 0, but if you multiply it by S, you obtain the seminorm in the limit space up to some constant. Now I want to mention some generalization of this fractional Sobolev spaces, yes, what is called the magnetic version of the spaces. It's a magnetic Laplacian, yes, which is defined in this way. Yes, this operator appears naturally, yes, when you want to describe the behavior of some particle which is under the influence of a magnetic field, yes, which is given in terms of this matrix A. So this is well known from the 50s, probably, or the 60s. Then in the mid-80s, this generalization of the magnetic Laplacian was given to analyze the behavior of relativistic particles which are under the influence of a magnetic field. So the suitable operator to describe the phenomenon is the magnetic fractional Laplacian, which is defined this way. Of course, when A is equal to 0, you record the fractional Laplacian. The space where to define weak solutions is the space WS2A, which is the set of functions N2 for which this quantity, this semi-norm, is bounded. In the limit case, when S is equal to 1, yes, the semi-norm is this one given in terms of the gradient, yes, for the space 1, 2A. So what happens when you send the parameter S to 0 or 1 in these kind of spaces? So as I mentioned, in 1986, Ichinose and Tamura introduced these magnetic fractional spaces. Then in 2016, Squasina and Bolzone, they studied the behavior of these spaces when S goes to 1. Yes, they proved the conversion of the spaces in a similar sense I mentioned before for the fractional spaces. Then the behavior when S goes to 0, yes, was analyzed in this paper in 2017 by Pinamonti, Squasina, and Becchi. Yes, they proved that the space WS2A goes to the space L2, yes, when S goes to 0, in a similar sense. Yes, the semi-norm times S goes to the norm of the limit space up to some dimensional constant. And then the generalization to P different than 2, yes, for any P bigger than 2, in fact, was given in this paper by Bush and Pinamonti, Squasina, and Becchi in 2019. Yes. They proved this to result for any value of P for the fractional magnetic P Laplacian. Now, I want to come back a moment to this slide. You see the bifurcation point. We have seen that the P Laplacian can be generalized in this way or this way. Yes, the G Laplacian of fractional P Laplacian. Now I want to mention one operator which is in some sense a generalization of these two operators, yes, in the sense which is non-local and with a non-standard behavior of the gradient. Yes, this operator is what we call the fractional G Laplacian. And it was studied in the first paper at the beginning, which I mentioned. Yes, this operator is defined this way. Yes, it's the fractional G Laplacian. It is non-local because of this integral in the whole space. And the non-local gradient has a non-standard growth behavior. It's because of this function G, yes, which is the derivative of a Young function capital G. Yes. The suitable space where to define weak solution of equations involving this type of operators is the space WSG, which is the set of functions in an Orlicz space LG, for which the non-local gradient is in LG with respect to some measure, yes, which is given in this way, or written in a more compact way, is a set of functions for which these two quantities is bounded. Yes, this quantity is this modular, and this quantity, this one. Let's observe that when G is a power, this is like the LP norm to the P, and this one is like the Gallardo semi-norm, SP to the P. Yes. If you want to obtain a Banach space, yes, how we can define the norm? As I mentioned at the beginning, you cannot define the norm in terms of these modulars because of the triangular inequality. So one way to define a norm is by using this Luxemburg norm, which is defined in this way in terms of modular. So this quantity satisfies the triangular inequality, and you obtain a Banach space. Yes, this space with this norm. So what about the behavior of these spaces when S goes to 0 or 1? So in the first paper I mentioned at the beginning, we study the behavior of the space WSG when S goes to 1. Yes. We obtain that in the limit, you obtain the space W1, but not the same function as in the case of powers. You obtain a different function, yes, the function W1 hat G, where hat G is a function, is in fact a Young function, yes, defined by this formula. Yes, although this function is different than G, these two functions are comparable. Yes, the function G and hat G define the same space. Yes, the same space W1G or 1 hat G. Yes. And the convergence is in the following sense. If you take the modular of the initial space times a correction term, you obtain the modular of the limit space. Sorry, here is the gradient of U. It's not U, because it's like the LP norm of the gradient in the case of powers. In fact, when G is a power, for instance, T to the P, the function G and hat G are the same function, T to the P. Yes. This result was proven when the function G satisfies the delta 2 condition. Yes. So when the function G has a bound in terms of some power function. Then this result was generalized by Alberico, Chunky, Pick, and Slavikova in 2020, where they proved the same result, but without assuming the delta 2 condition. It's for a more general set of functions, G. Then the behavior of the space WSG when S goes to 0, yes, was proven in this article and in this other article by, again, Alberico, Chunky, Pink, and Slavikova in 2020. And it was proven that the space WSG when S goes to 0, yes, recovered the space L hat G. Yes, again, you don't obtain the same function in the limit. Yes, this function hat G is defined by this formula. Yes. And the convergence is in a similar sense than before. The modular of the space times a correction term goes to the modular or the modular of the limit space. Yes. Again, this function hat G is a Young function and is comparable with the function G. Yes. In fact, in this second paper was proven that this inequality, this convergence is false if the function G does not satisfy the delta 2 condition. So it's a necessary condition. Now I want to state a generalization of this space WSG, yes, the magnetic version of this space, yes, which is the magnetic G Laplacian. Yes, a magnetic G Laplacian is an operator which is defined, yes, as the gradient of this no local energy functional. Of course, when A is equal to 0, you recover the previous space, the fractional Orlicz-Sobolev space. And when A is equal to 0 and G is a power, you recover the fractional P Laplacian. So in that sense, is the generalization. Yet this kind of operator could be suitable to analyze or to describe, yes, the movement of some particle, relativistic particle, which is under the influence of some magnetic field, yes, given in terms of this matrix A, and with a non-standard growth behavior of the gradient of this particle. So the natural space where to define solutions of these of equations involving this operator is the space WSGA, yes, which is the set of functions in LG for which this modular is bounded. Yes. Observe that now solutions are complex, yes, because of this matrix and the definition of the non-local gradient. So the the natural question is what happens when S goes to 1 in this kind of magnetic fractional spaces. Yes. So that question was answered in the second paper I mentioned at the beginning. If you assume that the Young function G satisfies this condition, yes, this condition means, roughly speaking, that the Young function is satisfying the delta 2 condition and also the conjugated function. Yes. So this means more or less that the function G is between two powers. Yes, there is a power which is bounded the function by above and another by below. So we prove that the space W as GA goes to the space, the limit space W1 tilde GA. Yes, and the convergence is in a similar sense than before. Yes, the function tilde G is given by this formula, which is the same than before, because when A is equal to 0, you recover the previous result. Yes, and of course, when A is equal to 0 and G is a power, you recover the result by Bourgain versus Amironecki. Yes, the key points of the proof, well, the proof is quite technical, but the idea is more or less simple. First, you study the behavior of the modulars, yes, of convolution of functions and truncations. So by studying these two kinds of functions, you can reduce the study or to study the result for smooth functions with compact support. Yes. So if you take a smooth function with compact support, first you can prove that if the function is in the limit space, you can bound the modular at level S, yes, in terms of these modulars for the limit space, and this constant which depend on S. So with this, you can prove that if you multiply this inequality by y minus S and you send S to 1, you obtain some bounded quantity. So this quantity is well defined in the limit. Now you can identify which is the limit. Yes, it's something bounded, but which is the limit? You want to obtain this modular. Yes. Recall that this expression is the integral, yes, of tilde G of the gradient of U, yes, the magnetic gradient. Yes. So the limit you expect to obtain, which is this quantity, is the integral of this quantity. Yes. The integral with respect to x of this expression is this one by definition. So how do you prove that? Yes, first you fix the value of x. Yes, and you proved, yes, by using some more or less technical computations that when s goes to 1, the integral of this expression is equal to this function. Yes. So if you can integrate again this expression with respect to y, you obtain the integral of this expression. Sorry, with respect to x. This one is y here. Sorry. If you integrate with respect to y this expression, you obtain the integral with respect to y of this expression, and you obtain then this modular. So this expression is obtained for a smooth function because of these previous computations, and then by using the dominating conversion theorem, yes, you can prove that you can integrate this expression and to interchange the limit and the integral, and then you obtain the result for smooth functions with compact support. Then by using some approximation arguments, yes, you obtain the result for an arbitrary function in the space. Yes, roughly speaking, that is the idea of the proof, the main idea. An important consequence of this result is the stability of solutions. Yes. In the following sense, if you consider the Poisson problem, yes, for this operator, yes, and you move in that solution the value of S, in the limit, the solution US, yes, which is the solution of this problem, goes to the solution of the limit problem with the limit operator, yes, which is the operator corresponding to the limit space, yes. The proof this kind of results is given in terms of the gamma conversions. Yes. You study the behavior of the energy functionals which are related to these operators, and you prove the gamma conversions of the energy functionals. It's quite technical, the proof. So I wanted only to mention the technique. Yes, the second main result I want to share with you is the behavior of these spaces when S goes to 0. Yes, again, if you assume the same condition on the Young function G, which is between the two powers, if you want, when S goes to 0, the space W SGA goes to the limit space L hat G. Yes, something similar to the case of the fractional spaces. And the function hat G is defined by this formula. And the conversions is in the similar sense. The seminar times correction terms go to the seminar of the limit space. Now, the proof is more technical than before, probably, because you have to be more careful, because in order to prove this type of result, first you have to prove some Hardy inequality for small values of S. Yes. So the critical point is to prove this kind of inequalities. Yes. Is technical because the function G is not homogeneous, so there are more technicalities in the middle. And another key point, yes, in order to connect this Hardy inequality with this problem, is this inequality, which is very useful, which is the diamagnetic inequality, which allows to connect this expression we see, which is complex, yes, with this one, which is real in some sense. So I think I want to finish now. So many thanks for your attention. Gracias por su atención.
Thank you very much for the talk.